Thank you very much. I'd just like to acknowledge two of my co-workers, Chris Holzapfel and Bill May. Chris has contributed a lot to this project since 2005. So what are producers looking for? Producers are looking for ways to maximize their crop inputs. They're looking for ways to uncover their field's inherent productivity, ways to manage spatial variability and crop inputs accordingly, and of course economic viability and prosperity. Let's talk a little bit about variability and precision farming. Spatial variability, really differences in production potential across a field. And the major causes are landscape characteristics, which are due to glacial activity, and there's not much you can do about that. Soil texture, soil physical, chemical, and biological properties, which is a function of the inherent parent material, but is also influenced by cropping practices. Soil and crop management history, and human activity, tillage, drainage, manure applications, all of these things affect spatial variability. When we talk about precision farming, there's a number of components: auto steer, sectional boom control on sprayers and seeders, yield monitoring, GPS guided field drainage applications, and of course variable rate application, and this is what I want to focus on. So what are the goals of precision farming? To actually understand the causes of spatial variability and to attempt to manage this spatial variability with some form of variable rate application. And so the challenge is really to quantify spatial variability and to do something about it. I just want to briefly touch on a precision farming project that we started in 1978, so I'm going to summarize 7 years of work in just a few slides here. This is where the site was located. This is the town of Indian Head. This is the research farm. We have two sections. And then our precision farming site was located a few miles from there. And this is land that's owned by the Indian Head Agricultural Research Foundation. And what we did is we split up the fields into 8 plots. They were roughly 38 acres each. And we went to a field scale research approach right off the bat. And the first thing we were interested in is establishing management zones. And the variable we used for establishing the zones was crop biomass, but we did this indirectly using satellite imagery and NDVI. So we used Landsat image over a number of years, and then from there we created a farm management zone map, and this is how it kind of broke down. Of course, predominantly dominated by one zone, but we did have a low and a high zone as well. And what we did is for a 3-year period is we checked the consistency of the zones from 1 year to the next. And what we found these are normalized yields because we've got different crops included in here, but what we actually found is that the zones were actually consistent over this 3-year period, and that the yields were always lower in the lower zone and intermediate in the medium zone and always higher in the higher zone. This is an aerial photograph of the field. You can see the 8 fields here, and you can see the little bit of a checkerboard display, and that's because we were doing different rates of nitrogen within each of those particular zones. When we did extensive soil sampling, and when we regrouped the soil samples based on characteristics of organic nitrogen and organic carbon, what we found is that indeed the levels of organic nitrogen that we observed followed the same pattern as the low, medium, and high yielding zones, and the same for organic carbon. And we convert organic nitrogen or carbon to organic matter. This is roughly what it boiled down to. The low zones had about 3.5% organic matter, and the high yielding zones about 4.2% yield organic matter. So what can we say also about nitrates and management zones? We did extensive samples, probably about 1,300 samples for a number of years over these, over the entire field, regrouped them. And basically what we found is that over a 7-year period, for the most part, there was very little difference in nitrates in the soil between the various zones. In some year, the high zones were a little bit lower. In some years, it was a little bit higher, but very, very low residual nitrates, except in, in 1 year here, they were a little bit higher, and that was because of a drier year. So if we do the average, this is roughly what the average nitrate values were across the zones over that 7-year period, pretty well indicating that trying to establish zones using residual nitrate is not really going to get you very far, and that's really the message that I was trying to show here. Some of the issues that we see with the current approaches to precision farming, and the biggest issue is that most approaches don't take into consideration temporal variability. And what is temporal variability? And temporal variability is simply the interaction of spatial variability, landscape and soil properties with weather. And probably another easy way of describing it is nutrient cycling is greatly affected by weather conditions. So if we go back to our little project here, where we show different amounts of organic nitrogen by zones, assuming that we had 1 pound per acre of 1% of the organic nitrogen being mineralized. So we're looking at anywhere from 35 to 40 pounds per acre per year being mineralized. If we had a 1.5%, it'd go from 53 to 60, and if we had 2%, it would be from 70 to 80 pounds of nitrogen per acre. So you can see that if you have the right temperature and moisture conditions, there can be a tremendous amount of release of nitrogen in any given year. So now if we look at our average soil residual nitrogen levels for the various zones, and then we add the various amount of nitrogen that could actually be released or cycled in any given year for like 1.5 or 2%, you can see that it can vary anywhere from 58 to 101 pounds per acre. So depending on the growing conditions and the residual nitrate levels in your soil, you almost have enough nitrogen being cycled from 1 year to the next to support a crop. And there lies the challenge of dealing with situations like this, because if you had a situation where you had a high turnover rate, you're looking at a lot of nitrogen, and if you happen to also put a lot of nitrogen down, like maybe 100 or 130 pounds, you could end up with a lot of excess nitrogen, and that becomes vulnerable for losses. And of course, there's big costs associated with that. So the future approaches to precision farming have to consider temporal variability. And this is where the GreenSeeker optical sensor comes in, not just the GreenSeeker, but other sensors as well that do the same thing, is that they're able to operate in real time, and they address not only spatial variability, but also temporal variability. So what is the GreenSeeker optical sensor? It's an optical sensing system that integrates with existing sprayer technology, and the sensors are used to draw inferences about the crop growth, and depending on the crop growth, you can make inference as to whether or not you have enough nutrients there to supply that potential growth. The sensor essentially generates light in 2 very specific wavelengths, and it's emitted through here, and they emit red light and near infrared light, and the reflection of the canopy is collected from this collector here. And what it does is it calculates normalized difference vegetation index, and everybody's very familiar with that, because if you have prescription maps being done for your farm, they're using NDVI from satellite imagery. In this case, we just generate it with the sensor. And again, NDVI is an indirect indicator of above ground biomass. The more biomass you have, the higher the NDVI value. And this has been known since the early 70s, since the early launches of the Landsat satellite. So I just want to briefly talk a little bit about how do we go about estimating yield potential. So what we need to do is we need to determine the appropriate growth stage, and we find that in cereals, anywhere from the 5-leaf to the early flag leaf, just starting to see the flag leaf emerge in cereals, and the 5-leaf to about maximum 5% flowering in canola would be sort of the optimum range that you would use, or crop growth stage. And the other thing too is that whatever NDVI value we generate from the sensor, we always divide it by growing degree days from the day of planting to the day before, or the day of sensing. And the reason why we need that is that so we can normalize the data and be able to compare one year to the next, because if you have a high NDVI value, unless you know how much time it took to grow that high NDVI value, then you really don't know where we're at, because we know that as the growing season progresses, the NDVI value increases because there's just more growth there. So we have to find a way to normalize that so we can compare from one year to the next, and this is why we use growing degree days. And Chris was the one that came up with that system as part of his graduate work. So when we look at integrated sensing and application, basically it's integrated into a sprayer, and this is the sprayer that iHarf has, is a little rogator, and basically it had the 8 sensors mounted onto the boom, on the front of the boom, and you can see there, I don't know if you can see it, but you can see the dribble bands of nitrogen here as we're going across the field. So let's talk a little bit about how we go about estimating N requirements. So first of all, if you can estimate the crop yields, the crop's yield potential, you can estimate roughly how much nitrogen is required to realize that potential. So if you have a potential of 60 bushels an acre of canola, we know that it requires X amount of pounds of nitrogen to be able to realize that potential. And so we estimate yield potential from the crop's biomass, which we measure with the sensor. And then we determine if there's a potential response to additional N fertilizer inputs using an N-rich reference strip. So if the NDVI of the N-rich crop or strip in the field is higher than the crop being evaluated, that means that there's a potential for a yield response to additional N added. So let's just run through an example to show you how that would work. So at a field level, what you would need to do is establish a nitrogen-rich strip somewhere in your field, and we recommend anywhere from 1.5 to 2 times the rate that you're normally applying in that field. If you're applying on average 50 or 60 pounds of nitrogen, we would ask that you double the rate for the nitrogen-rich strip, going from 100 to 120. If you're already adding maybe 120 or 110 or 120 pounds per acre, then maybe 150 or 160 would be adequate. Then what you need to do is you need to calculate growing degree days from seeding to day before sensing. So you'll have to have either an on-farm weather station or access to a localized weather station where you can generate that information, and that's not very difficult to do. And then you want to determine what the NDVI of your N-rich strip is, and also the farmer practice, the area of the field adjacent to the N-rich strip, to see what the relative differences are between what I call the farmer practice and the N-rich strip. And then you estimate the yield potential of both crops using NDVI and an empirical relationship that we have developed. And then depending on the magnitude of the difference in yield potential between the 2 crops, we apply the nitrogen accordingly. So let's run an example. This is the equation that we have come up with. It's an exponential function. So let's say that your N-rich strip is showing you the NDVI divided by growing degree days is here. You go across, it's giving us a yield potential of about 53 bushels per acre. And if you measure the farmer practice adjacent to the strip, you're seeing that it's about 45 bushels per acre. This is what the NDVI divided by growing degree days, and you go across and it gives you 45. Of course, the equipment is doing this on the fly. It's making these decisions. I'm just giving you one very specific example. So basically what we see is that the difference between the N-rich and the farmer practice is 8 bushels per acre. So if you have 8 bushels per acre difference based on this equation, assuming 14.5% grain protein, in this case we're dealing with hard red spring wheat, then you would add 12.2 pounds of nitrogen per acre. However, nitrogen use efficiency is not 100%. In this case, we set it at 50%. So therefore, you would have to apply 24 pounds of nitrogen to try to realize that extra 8 bushels of wheat. And I should make a note that when you have the commercial unit, this is a point where you can fine-tune. If you think that 50% is too high, then you can lower it to maybe 45 or 40%, and this will adjust your curve. So this allows the producer some fine-tuning, and very easily, just by tweaking that number a little bit. For lack of a better reason, we use 50%, but I know we have farmer cooperators that tend to use 40%. But again, over time, you kind of develop a feel for it. So what are some of the advantages of an optical sensor? First of all, they operate in real time, and that's really important because what it's doing, it's actually measuring plant characteristics, and it's measuring many plants over the entire field. And plants are very good at integrating the sum total of their experience to date. So everything that's happened into the soil, the sum total of the weather events is all encompassed in what the plant is giving you. So this is why this is a very robust measurements, because plants are very good at telling you exactly where they're at based on everything they've experienced to date. It's a relatively easy technology to use. And you can also, we think that it can be used for other applications. I'll give you some examples of that. So let me talk about some of the field scale wheat and canola trials that we did with that particular unit. And this is work that Chris did as part of his graduate work, many field trials. And we used it, we did the trials similarly to how a farmer would use the unit in the field with a few additional treatments to try to verify it a little bit closer. So basically the field trials consisted of a farmer practice, which is the rate that the farmer uses for that particular field. And then we also had a split fixed rate. Basically the farmer would apply 66% of his target rate, and then when we came in with the unit, we would then add a uniform rate of 34%. And then we would also have the variable rate with the GreenSeeker. So the producer was asked to at least apply 60% of the target N rate up front, and then we would use the GreenSeeker to top it up. And of course we had the N-rich strip, which was anywhere from 1.5 to 2 times the farmer practice rate. So I'll be using words like farmer practice and N-rich, so that just remember what that means. Farmer practice is basically what the farmer is, the decisions that, whatever decisions he made to arrive at that particular nitrogen rate in the field. So these are trials that we did with spring wheat in 2005 and 2006. And these are in actual farmers' fields. And if there's, what I want you to focus is just on the lines for farmer practice and variable rate. And you can see that in these particular trials, in all instances, we got similar yields with the farmer practice and the variable rate, except in one year we had a slight drop in yield. But if you look at the nitrogen, you can see that in all cases we were using less nitrogen. If we look at the canola field trials, in this case, we're essentially using less nitrogen, and in all years we were getting equivalent yields, except in this particular location we actually had a slightly higher yield with the GreenSeeker. And these are the other sets of trials. And of course, the whole idea with the GreenSeeker is to try to allocate the nitrogen more effectively based on plant characteristics. And we actually had situations where we actually added a little bit more nitrogen with the GreenSeeker. Not a whole lot, but a little bit more. But we still ended up with the same yields. So let's talk a little bit about the choice of nitrogen rates that the farmers were making with their farmer practice rates. If you look at the top line is the farmer practice, and the bottom line here is how much nitrogen we used in the enriched strip. And if you look at the yields, we found that in all situations, our farmer practice was yielding as much as the enriched strip, which means that the farmer was definitely maximizing yields with the nitrogen rates that he was using. Question is, even though he was maximizing yield, maybe he was still using a little bit too much. And again, here, if you look at between the farmer practice and the enriched strip for the rates, you can see that in all cases, well, of course, the enriched is always higher, but the yields were different. And in one case, the yield was a little bit higher with the enriched, which means that a little bit of yield was left behind. This is with canola. And again, you can see the differences in the amount of nitrogen used, and in most cases we were similar grain yields. In one year it was a little bit higher, in one year it was a little bit less, but very small in terms of absolute differences. So just to briefly mention some new studies that we're doing, these were field studies. We're also doing the same thing using small plots, and with small plots it's much easier to do, and we can do things a little bit differently. What we're interested in knowing is what's the impact of using the GreenSeeker on the same plots every year over time in terms of nitrogen use and grain yields. So here are the treatments. So we have two crops, spring and canola, and we just flipped wherever we had the canola plots one year, we put the spring wheat and vice versa. So in terms of treatments, we have a check, like a no nitrogen, because we're always interested if there's a response. We have an enriched plot. We have a farmer practice plot based on soil test, and we have a split N application where we put 66% of the farmer practice rate up front at seeding and the balance in crop. And then we also have one where we put 66% ahead at seeding, and then we determine with the sensor in crop whether we should add more nitrogen or not. And then we also have added another treatment where we look at the farmer practice. We have a plot which is the farmer practice rate of nitrogen. And then we just go in with the sensor and we determine whether or not we should add more nitrogen onto that farmer practice. And these are the 3 years that we've got for canola. And basically, this is how much nitrogen we used in the farmer practice, and this is how much was used with the GreenSeeker. And if we add the yields here, in all cases, the yields were equivalent. So we're able to obtain equivalent yields with lower nitrogen. And so we're looking at a difference of about 30 pounds of nitrogen. So at the current price of about 60 or 70 cents a pound, that's about a $15 to $20 savings. And in the case of spring wheat, again, this is how much nitrogen we used in the farmer practice, and this is how much we used with the GreenSeeker. And again, in all cases, we got equivalent yields. So we're able to maximize yields with a lower rate of nitrogen. Some of the disadvantages with the optical sensor. Well, first of all, it's another piece of technology to purchase, to learn about, to service, and to operate. And it does rely on post-emergent N applications. And it can conflict with herbicide applications. And it's an additional field operation which requires time and money. So addressing some of these disadvantages, it will require some familiarization with the technology. Like I said before, it's not complicated, but it does require some time to get familiar with it. In terms of probably the biggest thing is to understand how everything has to communicate together, especially if you're putting it on to existing equipment. And the other thing too is that you have to find a way to be able to calculate growing degree days, either from a on-farm weather station or else from a neighboring station that's maybe within 10 or 15 miles of your place. Post-emergent N applications, people would be a little bit hesitant about the effectiveness of post-emergent N applications. So if we go back to our trials, in this case is the spring wheat trials, you'll see that if we compare the farmer practice with the split fixed, you'll see that in one case we had slightly lower yields, and in the other case we had slightly higher yields. So it's not a foolproof system. In the case of canola, we were much more successful. Whenever there was a yield difference, it was always in favor of the split fix application of nitrogen. And this is the other canola trials, and in this case we got equivalent yields with the split fix application. If we talk about post-emergent N applications, we've been doing work with post-emergent or in-crop N applications since the early 2000s, so we've accumulated a lot of information, and our research shows that to reduce the risks of yield loss from in-crop applications of nitrogen, you have to put some nitrogen up front. We recommend a minimum of 60%. You can go as low as 50% of the total N fertilizer required as a starter nitrogen. Your choice is yours. With 66%, of course you're adding a little bit more, but you're giving yourself a little bit more buffer. And with spring wheat, we found that we could go in crop to at least the 5 to 6 leaf stage with no yield loss, and in canola up to the first appearance of first flowers. The reason with wheat you have to be a little bit careful, because wheat, once it starts to elongate, that's really the stage of maximum crop uptake. So if you're going to apply in-crop nitrogen, we suggest that you apply it at least at the 5 to 6 leaf stage. If you're concerned about timeliness or being able to get over your field, that's why adding a little bit more at seeding is going to give you a little bit more buffer. And the growth stages for the GreenSeeker actually correspond very well with the in-crop application that we've come up with, the stages. Conflicts with herbicide application. It's always a question of logistics, because you're using the same unit to do the GreenSeeker and you're using the same unit to apply the herbicide. You have to change your nozzles, so and then you're using nitrogen fertilizer as opposed to water and a herbicide. So you have to kind of work out the logistics for that. Each farm is very different in terms of logistics. And we find that it's a bigger issue on large farms because they tend to stretch their spray over a larger number of acres. And also there is some overlap between the time that you would be starting to use the GreenSeeker, and also it might overlap with herbicide applications with your later seeded crops. It represents another field operation. And I'm not so sure that producers are that interested in doing another field operation. So maybe you could also look at the sensor as a crop management tool. So you have your enriched strip, you have your farmer practice, and you go in the field and you say, okay, what is the sensor doing? All you'd have to do is, the way the unit is set up, you have 3 sensors on one side, 3 on the other, and you just drive the margins. You tell the unit which side is the enriched. You drive it and you stop, and it'll give you some information, and you can make a decision whether or not you should go over the whole field. And in this case, maybe just use an average N fertility package and then top up using optical sensor if necessary. So, some examples of other uses, it could be a good way to try to get an idea of what the yield predictions might be for cereals and canola. I'll give you just a quick example with spring wheat, canola, and oats, where we looked at NDVI measurement, predicted yield on June 19th, and this was what the actual grain yield was. So we were in that particular situation, we were very, very close. It doesn't always work out that way because we can't always predict what the weather conditions are going to be. There's still a lot of growing season left, but it does give you a pretty good idea. Using the sensor as an aid for applying in-crop dessicants in hummocky landscapes, that would be a very easy way to use the equipment. Simply as a tool for generating NDVI maps. When you're out applying fungicides in your cereal at the flag leaf stage, just do some mapping. If you're into applying a lot of manure, this would be a very useful tool. So is the GreenSeeker technology the answer? Well, the results we've obtained for real-time application has been very good and have demonstrated very well the potential of variable rate nitrogen with the GreenSeeker. And the optical sensor can account very well for spatial and temporal variability. It's easy to use, and it's a one-time cost. Once you've got it purchased, then away you go. If you're more interested in some information, simply Google nitrogen use efficiency, and you'll end up with this Oklahoma State University website, and it's got a lot of information. A lot of Chris and I's information is on this website. So I think time's up, so thank you very much for your attention and the invitation. Yeah, I'll do it. Yeah.